Hi everyone, welcome to your second lecture. We're continuing with our introductory unit, and in our last lecture we talked a little bit about what constitutes living things, which are the purview of the discipline of biology, right? So we talked about the 5 attributes that all living things have. We also talked a little bit about how we go about studying those living things using the scientific method. In today's lecture, what we're going to do is we're going to talk actually a little bit about chemistry in order to understand biology. And in particular, we're going to talk about the chemistry of water and carbon, because those are considered the chemical bases for life, at least on planet Earth. All right, so in this lecture, the things that I want you to take away, first of all, you're going to need to know something about atoms and how they're structured, ions and molecules. I'm also going to tell you a little bit about what an isotope is, because I know you guys hear that term and you probably wonder. All right, we're going to learn how atoms are bound together to form molecules, and then we're going to really focus in on the chemistry of water and carbon, since they are considered the chemical foundations of life. And then we'll finish out by talking about how chemistry might have led to the evolution of life. You know, last time we talked about where might the first cells have come from. Well, we're going to talk a little bit about where some of the chemical components of those first cells might have come from. All right, so let's talk a little bit about atoms. Now, again, this is getting into a little bit of chemistry, but you kind of need to understand this to understand biology. So what I have for you here is an excerpt from the periodic table of elements, and hopefully that's something that you've all seen before. So I've just got a few of the elements that are from that table. Now let's take a look at each of these. So each of these is a chemical symbol, these H or HE, these abbreviations that are abbreviations for the various elements. And then there will be numbers in these blocks that tell us something about each of these elements, okay? So let's take, for example, this first one here. This H is the chemical symbol for hydrogen, and then you see a number 1 and a number 1. So what do these numbers mean? Well, on the bottom, what you have is something called the atomic number, okay? The atomic number are the number of protons in that atom, all right? So what is a proton? A proton is simply a subatomic particle, okay, that is positively charged. So I'm going to draw it like that, all right? So our atomic number tells us the number of protons. And these protons occur in the nucleus of an atom. All right, what does this next number tell us? This right here. This next number is called the mass number, and the mass number is the number of protons, so that right there, plus the number of neutrons. So a neutron is another subatomic particle, okay, that occurs in the nucleus. So our mass number here is 1. We have 1 proton, and the number of protons plus neutrons equals 1. So what does that tell us? Well, in the nucleus of a hydrogen atom, there are no neutrons, just a single proton. So you probably remember from your earlier studies that there are 3 subatomic particles in an atom. There are protons, and those are positively charged, and there are neutrons. Now, let me see here, make sure I spell this right, neutrons. And they are neutrally charged, okay? And so I'm just going to put a 0 there, and I'm going to put that both of those things occur in the nucleus. But there's a third type of subatomic particle that you probably remember called an electron. And you probably remember that electrons are negative. Okay, and they are not in the nucleus, they orbit the nucleus in particular paths called shells or orbitals. And I'm just going to put a nuke, okay. So they orbit the nucleus. All right, so far in building this atom, we figured out that we have 1 proton, we figured out that we have no neutrons because we know that this number is derived by adding the number of protons to the number of neutrons. So if both these things equal 1, then there must not be any neutrons, right? Okay. Now, how do we get this number of electrons? Well, it turns out that an atom's most stable normal state is to have an electrochemically balanced situation. So if you've got one positive charge, an atom is happiest if it then balances that out with one negative charge, okay? So we have now built a hydrogen atom. Let's look at this atom, or sorry, this element here, this He, this is the chemical symbol for helium. So let's see if we can do a similar thing with helium. Let's start here with the number of protons, or the atomic number, okay? So the atomic number is 2. That tells us there are 2 protons. Protons are positive and they occur in the nucleus. So let's draw those in. 1, 2. Now, let's look at this number here, the mass number. The mass number is the number of protons plus the number of neutrons. We've drawn in 2 protons, but this mass number is 4, so that tells us that we must need, in order to create this particular atom, we must need 2 neutrons. And I'm just going to leave those empty because there's no electrical charge there, right? And again, we have 2 positive charges in the nucleus, and so we're going to want to balance that with 2 negative charges circling the nucleus. Okay, so I'm going to draw those like this. So a couple things to note. First of all, this mass number, this sort of implies that this is the weight of the atom, or the atomic mass of the atom. And so the mass number is made of protons and neutrons. So the majority of mass is contained in the atomic nucleus, and electrons have a negligible amount of mass. They're primarily just charges. They're just hard for us to conceptualize that, but they're just sort of like massless charges that are encircling this nucleus, right? The other thing that I want you to know is some terminology. The outermost orbit here in an atom is called the valence shell. And the electrons that occur on that valence shell are called valence electrons, all right? So I want to show you some features of these valence shells because they're going to become really important. So to do that, let's try building an atom using carbon, okay? So this C here is the chemical symbol for carbon, and I'm going to actually go to the next slide because I want some space to draw. So carbon was the chemical symbol, and the atomic number is 6, and the mass number is 12. Okay, so what does that tell us? Well, remember the atomic number is the number of protons. So we must have 6 protons in the nucleus. Let's draw them. So 1, 2, 3, 4, 5, 6. And I'm going to put plus signs so we know that these are positive charges. And we have a 12 for our mass number, and that is the number of protons plus neutrons. I've already drawn 6 protons, so I must need 6 neutrons to make 12 items in the nucleus, and that reaches our mass number of 12. Now, if I've got 6 positive charges, I need to balance that with 6 negative charges. So I'm going to draw an orbit here. I'm going to put an electron and an electron. Now, first thing I want you to notice is that, well, no, let me draw one more. Okay, then I'm going to draw another orbit. Okay, and so we've got 1, 2, so now I need 3, 4, 5, and 6. Okie doke. So I now have 6 items in the, or sorry, 6 protons in the nucleus as per this. I've got 12 particles overall in the nucleus as per our mass number. And to balance out our 6 positive charges, I've placed 6 negative charges in orbit around this nucleus. Now I want you to notice how I've placed them. First, notice that I put 2 on an inside orbital. Okay, this inside orbit, the maximum number of electrons that it can hold is 2. All right, but then once this inner electron orbit or electron shell is filled, we move on to an outer electron orbit or an outer electron shell, and the maximum number of electrons that there is space for in this shell is 8. You can actually have up to 8. Now, how many do we currently have in this valence shell? Remember, the outermost shell is called the valence shell. Turns out we have 1, 2, 3, 4 valence electrons, okay, in carbon. So what does that mean? That means that there are blank spaces here. I'm just going to put an X. Here, 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 and here. Think of these as like parking spots where 4 more electrons can go. So what does that mean? Well, it turns out that carbon could partner with other atoms to share electrons in 4 different places. In other words, carbon is capable of forming 4 bonds because it's got 4 parking spots in its outer shell. Let's look at another example. Let's talk about oxygen. Okay, I happen to know from years of study that oxygen, the chemical symbol is O, that the atomic number is 8, and that the mass number is 16, okay? So let's draw that particular item. So we've got, let's see here, 8, so we must have 8 protons. Let's draw those out. 1, 2, 3, 4, 5, 6, 7, 8, pluses, plus, plus, plus. All right, and then we know we have 16, so we've already drawn 8 protons. That must mean we need 8 neutrons to fill this out. I'm just gonna draw those bad boys in. Cool, now we're done with the nucleus. And if we have 8 positive charges, we need to balance that with 8 negative charges. So we're going to draw one shell. And remember, this innermost shell can only accept 2 electrons. That's 1, 2. But we need 8. So let's draw a second one. Let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we've got 8 positive charges, and we've got 1, 2, 3, 4, 5, 6, 7, 8 negative charges. But let's just look at this outer valence shell. To be happy and full, this outer shell likes to have a total of 8. So what we have are 2 empty parking spaces on this outer shell where oxygen is going to be capable of partnering with other atoms to share electrons, and it's going to be capable of forming 2 bonds. Okay, so things to take from this slide, or this two sets of slides. Remember that we have 3 different types of subatomic particles. I'm down here looking at your notes. You have protons, that's derived from the atomic number. You have neutrons, you get that from looking at the number of protons. You get that from the mass number, and then you look at the number of protons, subtract the 2, that's going to give you the number of neutrons. And then the electrons are going to balance out the protons, and they are going to occur in the valence shells. All right? Now, let's take a look at isotopes because I want to demonstrate something about protons. All right, so what is an isotope? An atom with a different number of neutrons is called an isotope. Let me show you what I mean. In this example, we have different, these are all nuclei. Let me do some erasing. I've marked on this in the past. Okay. All right, so these are all nuclei. In this example, we're not going to worry about the electrons for now. So these are just the nuclei of some carbon atoms, okay? So I want you to notice that for this carbon atom, carbon 12, we've got 6 protons and 6 neutrons. For this carbon atom, carbon 13, we've got 6 protons and 7 neutrons. For this carbon atom, carbon 14, we've got 6 protons and 8 neutrons. Each of these, with the differing amount of neutrons, are called isotopes. Now, one of the things that I hoped you noticed is that the number of protons stayed the same in each of these examples. The number of protons defines the atom or the element. So I'm going to put number of protons defines the element. So what do I mean? Well, if we suddenly went from 6 protons to 7 protons, it would be a whole different critter. Let's look up here. 6 protons is here. If you went to 7 protons, you wouldn't be carbon anymore. You would be nitrogen. So the number of neutrons can change, but if the number of protons change, then what you've done is you've changed elements, okay? So I always say that protons equal the personality of the atom because that's easy for me to remember. Right? Protons equals personality, letter P. Now, if you were to look at a periodic table, you would not usually see a mass number that was this perfect 12, 14, 16. You know, it's like no decimal points or anything like that. What you would normally see is an atomic mass, something like this, 12.01. Well, how in the world did they get that? Well, if you were to go out into the great big Earth and you could count all of the carbon that exists on the planet, what you would find is that about 98.9% of it is carbon 12. And it has 6 protons and 6 neutrons, sort of like our normal condition. But there's some small fraction of carbon that exists in the world that's anomalous. It's a little different. Instead of having 6 protons and 6 neutrons, it's got 6 protons, but 7 neutrons. And we can count them. 1, 2, 3, 4, 5, 6, 7. And if you were to look even more closely, you would find an even smaller number of carbon atoms that actually had 6 protons, but 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8. You can count them for yourself. If you were to average the atomic mass or the mass number of all of the carbons in the world, what would happen is that it would come out to be just over 12 because some of it is isotopes, okay? So that's why you often see these atomic mass numbers as greater than the norm, so to speak. Now, you've probably heard of radioactive isotopes, and what is that all about? Well, it turns out that, yep, you can have a different number of neutrons than protons in an atomic nucleus. But as you keep adding more and more neutrons, it makes the nucleus unstable. And what the atom wants to do is to get rid of the extra particles to become more stable. And so in order to do that, it's going to start ejecting some of this stuff spontaneously from the atomic nucleus, okay? So it might eject some of these neutrons. And when it does that, that is what's called radioactive decay. And I'm just gonna put rad for radioactive decay. And we all know that radioactivity can be very damaging. So why is that? Well, when these isotopes start to become unstable and they start to shoot off bits of the nucleus to become more stable, these bits that they shoot off act like atomic bullets. I'm just going to put bullets. Well, let me write over here. Yeah. And so you can think of it as like shooting through your tissue, and it does things like shred your DNA. So, you know, your DNA, if it gets shredded, it can cause things like cancer. And we know that exposure to radioactivity causes cancer. So that's how all of that works. So an isotope is just a version of an atom with a different number of neutrons than sort of the quote unquote normal condition. Now, do not confuse isotopes with ions. Ions are also a little bit different than normal, but instead of having an abnormal number of neutrons, ions have a different number of electrons. All right, let's look at how that might work. And so for this example, I want to look at sodium. So sodium has, it's got an atomic number of 11. So that means it's got 11 protons in its nucleus. And in a perfect world, the 11 positive charges of the nucleus want to balance with 11 negative charges of electrons. So let's look here. This is a normal sodium atom, and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. This is a normal sodium atom. But I want you to notice something. Remember how I told you that after you get past this first valence shell, all the subsequent valence shells, they like to have 8 electrons, right? So this valence shell is happy because it's got 2. This one's happy and stable because it's got 8. This outer one only has 1. It's got 7 empty parking spaces. Turns out that's kind of an unstable situation, and it's a pretty easy thing for other atoms to come along and snatch this electron away to fill some of their empty parking spaces in their valence shells. And so what happens is sodium has a tendency to lose its outer electron. Now let's look at this configuration. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We only have 10 electrons, right? 10 negative charges, but our valence shells are all full, and this is fairly stable. So this is what we call a sodium ion, because the charges do not match. And the way you would write that is Na+, okay? Let's look at hydrogen as another example. In hydrogen, you typically have an atomic number of 1. So in a perfect world, you have 1 proton and 1 electron. But remember, this is that first valence shell. To be happy, it needs 2 electrons to fill this up and be stable. So we have an empty parking spot here. Just like with sodium, it's pretty easy for other atoms to come along and snatch this electron to fill their empty valence shells. And when that happens, you end up with a hydrogen ion. It doesn't have any electrons, and you would write that like this, okay? Sometimes we use this a lot in biology, the H+, and sometimes we will call hydrogen ions, we'll just call them protons. So why is that? Well, because that's essentially what they are, right? They're just loose protons running around because there's no electron with them, okay? So later on in the course, we'll talk about proton pumps. Well, but we'll write the proton pump out as an H+. So protons and hydrogen ions are essentially synonymous for the purposes of this course, all right? So don't confuse ions and isotopes. Make sure you study that. All right, now let's move on and talk about molecules. Up until now, we've been discussing individual atoms, okay? But what happens if we start combining atoms together to fill up those parking spots? When you combine 2 or more atoms together, we're gonna call that a molecule. So here I have an oxygen molecule, all right? I've got 2 of the same kind of atom that are bound together. Now let's look at what's happening in their valence shells. So oxygen, remember I told you that its atomic number was 8. So it's got 8 protons in its nucleus, and that means that it's got 8 electrons orbiting its nucleus. So let's see here. We've got 1, 2, 3, 4, 5, 6, 7, 8. I'm going to draw a line right here, okay? And this is also an oxygen, and it's going to have 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, notice how these are drawn on top of each other. What's going on here? Well, remember that the ordinary oxygen would have 1, 2, 3, 4, 5, 6, 7, 8. And there would be 2 empty parking spots, right? And we want to fill those parking spots. So what these guys have done is they've scooted some electrons over so that they can share. This one's donated 2 and this one's donated 2, and they're sharing them in order to fill the valence shell. So now this behaves like a completely full complement of 8, and this behaves like a completely full complement of 8. This is an oxygen molecule, and it's formed a double bond like that. Is how we'll, we draw it like that, meaning that it's got 2 different places where it's sharing in order to fill its parking spot. Let's look at water. Water's kind of doing a similar thing, right? So if you remember, hydrogen had 1 electron in its outer valence shell, and I just told you that oxygen had 2. So can we see that what we have here is a situation where hydrogen is sharing its 1 electron and oxygen is sharing 1 of its electrons, and similarly that's happening here, and now everyone is happy. This is functioning like a fully stable valence shell, and this is functioning like a fully stable valence shell, all right? So these are examples of molecules. Now, sometimes molecules are compounds, and a compound are atoms from 2 or more elements. An element is just one kind of atom. So this is an element, right? And the reason is, even though it's a molecule, both those molecules are oxygen. So that's an element. But this is a compound because we have multiple atoms of multiple types. We've got water and oxygen. Here we've got, I think this is supposed to be oxygen and sodium to make salt, sodium and chloride maybe? Yeah, sodium and chloride. Okay, so that's going to be NaCl to make salt. And then this is going to be glucose, which is carbon, hydrogen, and oxygen. So we've got different kinds of elements and multiple atoms to make a compound. All right? So moving forward, in biology, we have some elements that come up over and over and over again. Okay, so these are hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. These are our most common elements. And then I have some questions for you down here. I think I probably already answered them. Let me go back. Boop. All right, let's look at my notes here. So note the blue boxed elements. Those are the most common ones that we find in biology. The interaction of electrons is what forms molecules, and we saw that on the previous slide. Note the number of valence electrons for each of these. So let's note the number of valence electrons here. Oxygen is missing 2, right? So it's got 2 parking spots. Nitrogen is missing 3, and carbon is missing 4. But notice how these are spaced, okay? What I want you to know is that carbon is kind of a more stable situation than oxygen or nitrogen. In other words, carbon is these are kind of evenly spaced, and it's going to be able to form 4 even bonds. Oxygen is going to be a little bit more of a heavy scavenger. It's got a heavier drive to fill this outer valence because it's only lacking 2. We're going to talk about that in terms of something called electronegativity, okay? If you can fill the outer valence, that makes things more stable. And so that's what we saw here, where they're sharing electrons to effectively fill that outer valence. What else did I want you to know? And then atoms bond with other atoms to fill their outer valence shell. So we've gone over all the things I wanted you to know for that slide. All right. Now, in thinking about how atoms go about sharing electrons with one another, there are 3 different types of shares or bonds that you can find in chemistry, okay? The first one is going to be what we call a nonpolar covalent bond, okay? Covalent meaning that these electrons are going to be shared, okay? So when you see the word covalent, that means that they're shared. Now, what does nonpolar mean? Well, remember how I showed you that the carbons were the electrons? Let me go back here for just a second. See how we've got 1, 2, 3, 4 electrons in carbon's valence shell, all right? So what they've drawn for you here is just the valence shell and electron, the valence electron shell. Okay, and we know that carbon has 4 of its own, and they tend to be evenly spaced apart from one another. And so if hydrogen, for example, were to come along and share, we have a situation where we're not tugging electrons in any particular direction, right? Everything is evenly spaced. That's not going to create a concentration of negative charges in one area. Everything is nice and even. So we're going to call this nonpolar, okay? Nonpolar. Now, let's contrast this with water. And I'm going to copy this for just a second. Hang tight, because I want to show you guys something. All right, back here. All right, let me paste that so we can look at these side by side. Okay, so we have an oxygen here, and remember, oxygen only had 2 parking spots left, right? We don't have the same situation where things are evenly spaced. Let me go back to my draw. We don't have the situation where things are evenly spaced. So if we look here, when oxygen is bonding with hydrogen to try and fill its valence shells, what do you notice about where the majority of the electrons are concentrated? The majority of electrons are concentrated here around the oxygen, aren't they? And remember, these electrons carry with them a negative charge. I've turned this picture sideways, but that's supposed to be a minus sign. So what that means is that this side of the molecule is a little bit more negative. It's pulled these electrons away, and then these ends are a little bit more positive because, again, all of the electrons are concentrated down here. Now, they are still sharing in order to complete their valence shells, but they're not sharing equally, okay? So this is a polar situation because we have a negative pole and a positive pole, kind of like a magnet. And oxygen is what we call electronegative, okay? So here it's showing me that we have a positive end on the hydrogen, and we have a negative end on this oxygen, and a positive end on this hydrogen, and a negative end on this oxygen. Now, what I want you to notice is, what do you know about magnets? Negatives and positives attract one another, don't they? So water molecules stick to each other the same way that magnets do, okay? Do you see these little dotted lines? These are supposed to represent magnetic attractions. And I think I mentioned this in a later slide, but I'm going to say it now. These little magnetic attractions are actually called hydrogen bonds. Okay, so that's going to be important when we start talking about the chemistry of water. This isn't an actual chemical bond. We're not sharing electrons. This is just a magnetic attraction. The sharing of electrons is happening here and here, here and here. Okay, so that's a polar covalent bond. So 1 was nonpolar, 2 is polar, and both of these are covalent, meaning they're actually sharing electrons. Now, let's look at a third type of bond called an ionic bond. Remember me telling you that ions were when you didn't have the right number of electrons in your atom? Well, what's going on with an ionic bond? remember me telling you, I'm going to go back here, where I told you that sodium was unstable because it only had like this one lonesome electron hanging out here, and it needed 7 more to complete this valence shell. So this is actually pretty unstable, and it's very easy to get this snatched off. Now let's go back here. Here's that same sodium atom, and we're looking just at the valence shell, and we've got 1 electron. Now let's look at chlorine, all right? Chlorine, actually, it turns out in its valence, it has 1, 2, 3, 4, 5, 6, 7, and it only needs 1 more to fill up its valence shell. So it's electron hungry. It's going to scavenge electrons, and this is going to give up electrons. And so what happens in an ionic bond is one atom completely snatches the electron from the other. There is no sharing at all, okay? So then you may be asking yourself, well, then how does salt stay together? If these aren't actually bound together by sharing, how does this stay together at all? Well, remember, when you snatch this off, this becomes positively charged because there's more protons than electrons, and this one now is going to have more electrons than protons. So this is going to be positive, this is going to be negative. It's held together by electromagnetic forces, basically like a magnetic attraction. Okay, so that's an ionic bond, okay? And I want you to know the difference in those 3 types of bonds. All right, let's see here. This is just another way of looking at it. Okay, so here we have nonpolar covalent bond, nonpolar covalent bond. Okay, can you see that like here we have these being pretty evenly shared. Here, these are pretty evenly shared because if you were to draw this out, you'd also have boom, 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 right? 3, 4, 5, 6. So that would be very evenly shared. But here, again, this is that water molecule, and it's going to be unevenly shared because we're going to have the oxygen sort of like gobbling up and not being evenly shared. We have a concentration of electrons around oxygen. Okay, so let's see here. I'm going to stop this lecture. There's a part 2 of chapter 2 coming, but I think this is a natural stopping point for you to wrap your mind around this general chemistry review, have a snack, and then I want you to pick back up with part 2 in just a few minutes. All right, bye-bye.